Hello and welcome to Alchemist Camp, where we learn Elixir by building things. Last time we built out a state module for our tic-tac-toe game, and it includes essentially a state machine. It's got that state in status, so that could be the initial state of a game, the state of choosing who goes first, the playing state, game over state, and then after game over, winner reported state. And we used functional pattern matching to deal with the states coming in a fairly robust and easy to reason about way. And this time we are going to do two things. We're going to make the tic-tac-toe module work with the state module, and we've made a new module called CLI, the first user interface we make for the tic-tac-toe game. Later, after we've learned Phoenix, we'll probably make a web-based one that'll be a little bit easier to work with. The first thing we'll do in the CLI after aliasing state and itself is we'll make a play function. And this will kick off the entire app. This will call tic-tac.start, which we haven't defined yet, and it'll pass a function that the start function will take in to use to handle the game. And any UI module we make to work with tic-tac will have to use this interface. So we'll put more in it later. For now, we'll just handle the first state. So handle state status initial, and the message from the main tic-tac-toe module we'll call get player. This is different from the actions in the state module. This is, instead of an action for the state, this is something being requested of the UI. In this case, it's to get the first player. So io.get which player will go first, X or O. And we'll pipe the response from that to string.trim. And we'll turn it into an atom, since the rest of the game uses the atoms X and O for the players. Okay, and we need to make the start function. And it takes a UI. Okay, game equals state.new UI. And as you may recall from last time, the UI is one of the fields in a state. It's nil by default, but if we pass the new a UI, then the UI will be in the state. So from now on, anytime in the game, anything that has access to the state, which is almost anything we call, we'll be able to type UI.handle and call the UI handler. Let's save this here and jump into IEX. Okay, game is unused, that's fine. So we'll start the game from CLI, play. Tic-tac.start, CLI handle 2. That should be fine. Oh, tic-tac also needs access to state. Tic-tac square and state. And recompile. Okay, so it returned an OK, and then a tic-tac state that has a board we're used to seeing, as well as a UI that we can get at. Go back to the CLI. The next thing we want to make is actually we need a helper for showing parts of the board, because a board like this is a little bit difficult to work with. We'd almost have to create a new tic-tac square with a column and row and then use that to access it. So instead of that, let's make a helper here. We'll call it show, and it will get a column and a row out of the board. And just to make sure we've got this right, board equals g.board. Board is a map of maps, essentially. The easiest way to get at a nested attribute is with for and with comprehensions. So for, we'll just do the high level first, key and value from board do value. Okay, we'll do the keys. Now this is really cool. This is something that I really miss whenever I'm working with JavaScript or another language I haven't done in a while. You can use nested pattern matches. So get a key. So instead of this key, we're going to get the sub properties out of it, which are column and row. We can say just get me the columns, or just get me the rows. That's pretty cool. I think we could just do this maybe. Yeah, and we could do we could put limits on it, and also we could get the pairs of columns and rows, which is probably a useful thing to do as well. So we will grab an item. It's for column, row, value from board column equals C and row equals R. Do V. And then if the item is empty, we'll just show a blank space. And if it's an X or if it's an O, we'll just toString it. Recompile. Keyword argument must be followed. Yes. Okay, and we've still got a board in memory. Import tic-tac.cli for convenience and show board 2, 3. It's empty. They're all empty. Okay, this looks like at least we've got the board parsing logic. Now we'll make a display board. Display board that just takes in a board. We'll call it B because we need it to be brief. io.puts, and we'll just do a multi-line string and end it there. Show board 1, 1. And then we'll show board column 2, row 1. And we'll separate them with vertical pipes like so. Copy that twice. And let's see, 1 for the square, 2 for the pipe, square, pipe, square. And copy this as well. All right, and these are going to be 2s, and these are going to be 3s. Okay, that should print out the whole board. Okay, now we'll display board. One, two, oh, because of those spaces, it'll be 1, 2, 3, 4, 5, 6, 7, 8. That's better. Add one more. Okay, we can now display the board. Good for that. And let's go back to the main tic-tac. So what we want to do is we want to get OK in a game, then we've got to get a player. So that'll just be player equals UI.game get player, and then we're going to run that by the state machine, because the only way we can change between game states like initial or playing and game over is by going through the state machine. State.event game choose P1, and we'll pass in the player that we got from the CLI, and then we're going to handle the response we've got, or we're going to handle the current state we have in our game and decide what to do, like what to pass to the state machine or what to pass to the UI. But before that, we're just going to print out the game. Recompile. Tic-tac is missing. So it is. Okay, so CLI.start. Oh, it's called play, and I've imported it. Okay, X will go first. And status is it's X's turn. Okay, that's not bad. And the UI got the handler. All right, so the next thing we want to do is handle the game, and we're going to make a new function to do that, and this is going to be the main workhorse of the module. Handle status playing. We don't need to handle initial because that's done from the very beginning. And we're going to store the game in, or we're going to capture the game in a variable. Request a move from the UI. And then if we got a valid column and row, then we want to pass that off to play at, which goes through all of this to make sure it's a valid player and square and piece and all that. Then we want to run it through the state machine, and then we want to handle how things currently are again. So we're going to use a with column and row that we get from game.ui, since we've stored the UI inside our main state. We've got access to it at all times. Game.ui dot, and remember the UI dot is the handler, request move, and we'll stop for there for now. And then we expect an OK and a board, or we will make it so that an OK and a board come back from the handler. And play at game.board, because play at only takes a board, not the whole game state. Game.board, column and row, which we captured from the request move. And then the player, since play at requires a player, so we'll get the player out of the game state as well. The game.turn, and then we'll pass that off to the state machine, which should return a game again. Dot event game with the updated board that we got from the play at. Play, and what does it take again? It takes a player. So play, we have a game.turn. And for now, we'll just output the game. Okay, that's a lot of stuff that could go wrong, including this request move, which isn't even handled yet. So let's write that and then we'll test it. But now it's going to be state status playing. We'll store that in a variable. Request move. First thing we'll do when getting a move is display the board. And we'll state.board io.puts what's state.turns. So this is going to be either X or O. Move. And this is going to kind of suck, but we'll get the column and the row from them separately. Column. And then we don't want the string 1 if they put column 1. We want the integer. So let's say string.trim, string.to integer. And then we'll do the same thing for row. And then we'll just return the column and the row. All right, recompile. Boom. Excellent. We'll start a game. Play a game, that is. O will go first. Now let's handle that status. Play. O, 2, 2. Okay. Tic-tac dot handle. Ah, then that looks nice, relatively speaking. And it said a no. Okay. Boom. Next thing we got to do is make this call a handler again. So let's go to the top of our start function, and we'll use a with to streamline this, and we'll add a handle at the end. So with OK and game from state new.ui. The reason for the with here is just so that if any of these do have an error, the error will get spit out at the bottom instead of causing something to crash. Okay, get the player from the UI and game.getPlayer. Then we get OK and game from state event. And it's okay that we got game twice. This game comes from here and is used here. And then this game is rebound to the value returned from this function. So then we do handle game, because remember game is just the state of everything, else error error. So we'll just print out the error and we can experiment with that. Recompile it. Error, that's right. Oh, need commas. Okay. And we'll just play. X goes first. I'm going to say the move is 5, 4, invalid square. Excellent. Let's play again. X goes first, 1, 1. Okay, that's good. Why did this not get handled? Ah, it's still not calling the handle, so we've just got to add that in here. So instead of do game, it'll be do handle game. And we'll do the same as we did above, else just return the error. Okay, this is pretty much playable now. Of course, it'll never end. Should have ended there, but we get the idea. All right. Yeah, can't have an empty argument. That actually is a little tougher. Binary to integer, not taking care of it. Let's make a little function for this. We'll call it trimmed int. Trimmed int, and it comes from a string. Case of integer dot parse of the string. That should handle the trim for us actually. Do okay, a number will be number. There, consistent, let's call them both error. Okay, and then we're going to use trimmed int on both of these. Trimmed int. Compile and play. X will go first and enter nothing. Error, invalid square. Much better. Okay. Now that that is done, the next thing we'll do is do a win check. And the win check will not return an OK in a game. It's just going to return a single variable that says if the player won or not. And that function will need, we haven't made it yet, but it will need the board and the player. And then we'll pass that to the state machine, which will return OK and the game, like the state machine always does. We'll pass it the game and check for winner with the result we got from our win check function. And that's going to have to be either X or O or I believe just false. I think anything, let's check that really quick. X, O, or invalid. So anything but X or O. So we'll just make it X, O, or false. All right. And after we've passed that off to the state machine, then we need to see if the game is over. Possible someone didn't win, but the game is still over, because the board could be full. So we'll make that a separate step. Just get a single variable back. And we'll call this function game over. State.event of game and game over, passing it the over, whatever we got there. So either over or game over or not over are the two possibilities. And then we'll handle the game. We need one more handler, and this will handle game over. And that will be game UI game. So we'll just do game and null. With that out of the way, we just need to write the win check helper functions in order to do the win check, check for game over, which should be really easy, and make sure everything is hooked up properly. Let's start with the helpers for the win check. So basically we're going to need to check all the columns and all the rows and the diagonals to see if there was a win. So we'll just make some functions called get column, get row, and get diagonals that will get whatever was in them. And then we'll make a separate function to see if there was a win on a given line. So first is get column, takes a board and a column. And the easiest way to do this is probably with comprehensions again. So we'll do for column C and row R. And that's the value, key value pair. So that value is going to be like empty or X or O. And well, actually, let's do this in the terminal. For call C row R and value the board, do V. This should get them all. Board is called B here. Okay, yep, so that got a bunch of empties like it should. So we can restrict that to R equals 2, and we should just get 3 now. We will do that. Do V. So if we're getting a column, that means the column is held constant, and we don't need to use this row. We'll say column equals C. Do V, so that will get a list of the elements in that column. And then the same thing will work for rows. So we'll copy this down here and change column to row. And in this case, we don't care what the column is, and we want to hold the row constant. And row must equal R. So we'll get those 3. Then to get the diagonals is a little bit trickier. The diagonals are going to be location 1, 3, 2, 2, and 3, 1. That would be one diagonal. Then the other diagonal would be location 1, 1, 2, 2, and 3, 3. So that one's pretty simple. We'll do, actually we'll do them both together. Get diagonals, board do. Get some more space here. So first one will just be for column C and row R, the value. We will get everything from the board where C is equal to R. So we get a list of one diagonal and a list of the other. And just to be safe, better put these in parentheses so this doesn't get parsed wrong. Okay, and I'll just copy that line down. And this one, instead of C being equal to R, C plus R has to be equal to 4. That would get the 1, 3, 2, 2, 3, 1 diagonal. And that should be it. Recompile. Oh, that's going to break because we've got all kinds of undefined things. So the win check is still going to need some more help. We're going to need a function that tells if a line was 1 or not. So this get column is going to return something like x, x, o, or empty, empty, x. And the get row will do the same thing. And the get diagonals will return 2 lists. In any case, we're going to have lists with 3 elements in them, which represent one line. It might be a row, it might be a column, but we just want to know if they all have the same thing in them. Like if they're all x, then x1, because it had that row or column or diagonal, or if they're all o, then o1. So we will make a function called oneLine, and it will check to see if they're all the same. We can test an IEX. So we're going to use enum.all on a line, say like x, x, empty. And if they're all the same, we return the value. So in this case, we're looking for x and equal to 1, which is just the list element. And it's got a question mark in it. So that's false. Now it's true. So we'll make our oneLine function at the bottom. oneLine, line and player, do enum.all, line and player must be equal to each of the elements in the list. Now that we've got a one line, we can do a win check that uses our get column, our get row, and our get diagonals. I think it'd be a good idea at the end of the episode to go back, load up the code in your own terminal, and play around with it. Unless you're really comfortable with higher order functions, this could be a little bit confusing and dense. So, right, we'll make the win check function now. Win check. It's going to take the board and the player that we're checking to see if won, which we can just grab from the state. The columns will be enum.map 1 to 3, because that's how many columns there are. And we'll use our get column, board, and 1. Just in case you're not used to quite this kind of syntax, this is the same thing as if we did this, which is also the same as if we did this. So this will map over the numbers from 1 through 3. For each one, it will transform that number into a list of the items in that column number. So we'll have a list of X's and O's. Will be 3 of them, 1 for each spot in column 1, followed by a list of the values in column 2, followed by the list of the values in column 3. And we'll do the same thing for rows. That's pretty straightforward. And then diagonals, our function already returns a list of 3 elements for the first diagonal and then 1 for the second diagonal wrapped in a list. So it's already done for us. So we have a list of 3 lists, a list of 3 lists, and a list of 2 lists. The way we append lists to each other is with the ++. The quickest way to show you in the terminal is like this. And you see it put the 2 lists together. And if you had a list of lists, and you appended that to another list of lists, it simply puts the list of lists together. Okay. The win status is going to be enum.any, which is basically any winning line out of columns, rows, and diagonals. So this is 8 different lines we're checking one by one, and the enum.any, or the function we're passing enum.any, is one line and the player, because one line uses a player. So if the player we passed into board has won on any of the lines, this win will be true. And if it hasn't, it will be false. And we need to return the player instead of returning true. So we're going to say if win do player else false. Okay, that is by far the hardest part. Let's see where we are on recompiling. Not too far. So initial is unused, and we haven't defined. Oh, well, that's easy enough. The player is, we got to get the player before this state event changes the next player turn. So we're going to get the player here. Equals game dot turn. Okay, now we've got a player to check. Board, I believe we do. We don't have an over, we don't have a 1. We do have a 1. The win check is done, so we need to make a game over. There we go. And that just needs a game. And there are two ways a game could be over. The game could be over if there's already a winner, which we have in the game state right here, or the game could be over if the board is full. So we'll figure out board full. So the board is just 9 squares, and each square can be pattern matched with a key and a value, like we've been doing right down here. That's basically a key and then a value. We just need to look at the values, because if any of them are empty, then the board's not full. If all of them are X's or O's, then it is full. So use enum.all. And then the function we'll use as our test is going to pattern match on the squares and just take the values. And we'll look for a value that's not empty. So if every single square on the board is not empty, then the board is full. And then if the board is full, or game.winner, and an X or an O will match as true. Nil or false will be false. Game over, else not over. Okay, compile again. Okay, so line 48. Oh, game over should be a question mark. Wow, all of that compiled. Let's play. Start. X will go first. 1, 1. That's invalid. What? Okay, so we broke something there. Let's look at the handle. Play the turn. Yep. Win, check, board, and player. Well, it's gotta be in here. The other functions all work. Like we've got a board. We can do get call of board and 1, 2, 3. Give a really bad input. We just get an empty list. So let's look at what's going on here. X 2, 2. Oh, that's because of this trimmed int function that we made. So we'll say string. We'll go into string dot trim and into dot to integer. And let's see if that makes sense first. String dot trim string dot to integer. Yes. Excellent. X will go first. 1, 1. Bad argument and arithmetic expression. EX77. Missing a plus. Invalid winner. This is just something we haven't updated since 2 episodes ago. Alright, so pass back an X or an O, and we should be able to take a false. We'll just say if it's false, then because there doesn't have to be a winner, and state with no changes. If there is a winner, I think that's good. It would also be nice to set the turn to nil. What we'll do is we'll make a win state here, just because the lines are getting really long, plus turn nil, because there is no one else. It's no one's turn after someone has won the game. And these two will become win state. You know, actually, I think on any input it should do this. Really, it shouldn't have to be false. This is looking pretty good. X is going to throw the game here just so we can see how it goes. Okay, invalid state transition, game over, status, game over. So we'll just make another handler. And event state status game over. And we're going to ignore the results of message because the game is already over. It can't become extra over, and it can't become not over. So whatever the result there is, we will just return OK and the state. That way we don't have to worry about setting the game to be over twice. Okay, that's good. So we just haven't handled it in a CLI. So we'll just add that. Handle state status is game over. And we'll save that in state. And then we will display the board. Otherwise it looks like the game isn't really over. State.winner, do tie, say another tie. That's what's wrong with this game, and it is what's wrong with tic-tac-toe. And anything else, player state.winner is victorious. Okay, maybe we shouldn't make them both that exciting. Winning is actually exciting in tic-tac-toe, because you do not expect that to happen. All right. Recompile. Then we're also going to need a nil here. Or actually anything. We're not using any message at all. We're just getting the game over information out of the state. Yes. All right. We'll check the tie state. And ties work. This is a good spot to wrap it up. The important thing about this project is just the modularity of it. If we were to ever make a different interface to play the game from, like a web interface, the only thing that would have to be changed is the CLI module. Everything that works now would keep working with a different UI. We would just have a different UI module that would call start UI, just like the CLI UI module is. So all of the communication is happening through tuples, and as long as the status is conform to the system we set up, it's pretty modular and easy to replace. And the way this program is designed also makes it incredibly easy to test. Since all of the functions are pure, meaning given the same input, they will always have the same output, we can test anything that could possibly happen at any point of the game, whether valid or causing an error, simply by passing the correct state and parameters into the right function. And that's very different than the typical experiences debugging games or even simpler web apps, where there's a whole bunch of state being stored somewhere. So calling a given function with a certain set of parameters might usually work, but not if the user had done something strange beforehand that put the system into an unanticipated state. And let's recap a little bit about what we've covered in this project. It's by far the biggest one that's been on this channel so far. We have multiple modules. We're executing functions passed from one module to another, like here. We're using module structs with default values. We're doing extensive pattern matching. And for some of you, this may have been the most complex comprehensions and filtering you've seen, especially if you didn't check out the solution to challenge number 8 video. So I realized this was quite a meaty lesson for some of you, especially if you're not used to dealing with higher order functions or passing state around all over the place, or state machines, or over-engineered tic-tac-toes, anything like that. So I definitely will put source code up on alchemist.camp soon. As you know, the site is being built as I make these videos, just because I have limited time to work on all this, but it's only gonna get better. And the challenge for this time is hopefully something that will help out with parsing data and dealing with that. So using the square module that we've already been using for all of this tic-tac-toe, where we have this row, column setup, make a function like we have in tic-tac-toe for getting the columns or getting the rows or getting the diagonals, but instead have it work on an 8x8 board and make one function that gets everything that would be under attack from a piece at a given position if it were a chess rook. Make another one to see all the squares that are being attacked by a chess bishop, and make another one that will see all the squares that would be attacked by a chess knight. Have fun with that one, and until next time, code on.